Hello, I'm Ketan Goel. I'm pursuing MTech Structural Engineering from VIT University Chennai campus. Today I'm going to tell you about buckling of shells. So we will see a small introduction and then equilibrium equation for buckling. So in introduction, for thin shells, a thorough treatment of shell stability should include a study of spherical shell under external pressure as well as cylindrical shell subject to axial compression, external pressure and torsion. A real, slightly imperfect column and plates do buckle at critical stress predicted by the linear theory. But real imperfect axially compressed cylindrical shell buckle at a stress significantly below that is given by linear theory. So that thing is given by linear theory. It is aspect of behavior of axially compressed cylinder that makes them especially worthy our attention. So this is the thing which gains our attention for this study. Before considering the stability of axially compressed thin cylinder shell, a few words regarding the behavior of thin shell in general are in order. So before we move to the study, some points are there which we always keep into mind while going for buckling of shells. The primary difference between the shell and plate is that the shell has a curvature in the unstressed state. So when it is in unstressed state, the shell will have a curve, whereas the plate is assumed to be initially flat. So plate we always assume to be flat, but the shell, it is when in unstressed state we consider it as a curve. Then as flexure is concerned, the presence of initial curvature is of little consequence. However, the curvature does not affect the membrane behavior of the surface significantly. Membrane action in a surface is caused by in-plane force. These forces may be primarily forces caused by applying edge loads and edge deformations, or they may be secondary forces resulting from the flexural deformations. And if the surface is initially flat, secondary in-plane forces do not give rise to appreciable membrane action unless the bending deformation are fairly large. On the other hand, if the surface has an initial curvature, the membrane action caused by secondary in-plane forces will be significant regardless of the magnitude of the bending deformation. So this will be in the case of shells, and it won't be there in the cases of plates. Membrane action resulting from the secondary middle surface forces is therefore accounted for both small and large deformation studies of a shell. As I told you, these all the things will be considered in case of shells. So moving to the linear theory of cylindrical shell, in this we will see the linear theory of cylindrical shells, and which is done using Donnell's equation. So in this derivation of shell equation, there are lots of shells equations available. The problem is that in this we encounter several terms which are relatively very small in magnitude. So if these terms are all retained, the solution of the equations becomes so involved that the equations are of little practical use. There are lots of small terms which are there in this equation. Therefore, basically we should ignore it. So most investigators have therefore decided to omit some of these terms. So most of these terms which are not very much useful, that we can remove or neglect. The result of the situation is that there have been developed a various shell equations, each based on different set of simplifications. So different people have done different calculations by ignoring different these small variables. So lots of theories are developed because of this by considering different set of simplifications. So in the equation which we are going to see, that is Ronald's equation. So this equation is relatively uncomplicated, and they have been shown to give satisfactory result when used to deal with buckling problems. Okay. So this linear theory, in this we have various shell equations, each based on different set of simplification, as I told you. So in this study, the which is demonstrated below, the audience have suggested the simple way of developing the theory of thin shells is to start with the relationship already obtained from the thin plates and to revise this whatever necessary. So theory for plates is which one we have. So doing a little simplification in that or little variation in that, we will develop a theory for cylindrical shells. So we will develop a theory for shells or equations for shell from the basic equations that we have for plates by doing little modifications in those. In deriving the Donald's equation, we have to make the following assumptions. So the assumption number one will be the thickness of the shell is small as compared to the other dimension of the shell. That is, the shell is thin. So we have three dimensions. So as compared to length and breadth, the thickness that we consider will be very small. Then second one is lateral deformation are small as compared to the thickness of shell. Whatever thickness we are considering, it is already very small, and the lateral deflections are again much smaller than this thickness of the shell. Then third one is the material from which the shell is to be constructed is homogeneous, isotropic, and the one which obeys Hooke's law. Homogeneous is the one which is made from a single material. Isotropic is the material which have same properties in all the direction. And Hooke's law, as we know, the strain relationship will be linear. Then fourth one is lines normal to the middle surface before bending remain straight and normal during bending. Fifth one is the shell is initially a perfect cylinder and it is loaded concentrically at every cross section. So the shell is, as I told you, it will be initially a perfect cylinder, and when it is loaded concentrically, it should be loaded concentrically at every cross section. So moving to the derivation part, we need to keep in mind all the assumptions. Okay, so from these figures that are given, let us consider a differential shell element of thickness h as shown in figure and having the radius of curvature r. This radius of curvature r, thickness h. The coordinate system chosen is that the origin is in the middle of the surface of the shell and the axis is parallel to the axis of cylinder. Then y-axis is tangent to the circular arc and the z-axis is here, this one. The z-axis is this, which is normal to the median surface. Okay. Then here we will use the circumferential coordinate y instead of an angular coordinate, which facilitates comparison between the shell and the plate. So by considering the circumferential coordinate y, we can differentiate in between plate and shell, which we will see in further equations. Displacement of the shell are described by their components u and v and w in the x, y and z directions respectively, as indicated in the figure. The forces acting on the shell element consist of the in-plane forces depicted in figure this second figure B. It is depicted in this figure all the forces acting on the element, and the transfer, shear and bending are indicated in this figure. Also the testing moments are represented here. Then moving towards equilibrium equations. So in today's presentation we will see only equilibrium equations. So the equation of equilibrium in the x and y directions are considerably simplified if the curvature of the surface in these two directions, both initial and due to bending, is neglected. So we have to neglect this thing. Curvature of the surface we have to neglect. In other words, we assume that the transverse shear forces have negligible components in the x and y directions, and that the component of the in-plane forces in the direction are equal to the forces themselves. Thus the equilibrium equation in x and y direction for the shell are identical for those which we obtained for the plates, and for convenience these equations are replaced here. So these are the same equation that we use in plates. Equilibrium equation for plates. These are the same equations that we are going to use for cylindrical shells. Then to obtain the equation of equilibrium in z direction. So these are the one in x and y directions. So in z direction, for z direction it is necessary to take curvature. So in z direction there will be the curvature. So now we are going to consider the curvature effect. The two equations that shown above are for x and y direction. So x and y direction will be same as for plates, as no curvature will be there in plate. But here we have to consider the curvature effect. So that will be in z direction. So it is necessary to take the curvature of the element into account. Both initial curvature and curvature due to bending must be considered. Due to initial curvature of the shell, the force Ny is, as indicated in the figure, have a component in z direction which is equal to this. This will be the z component. So for generating component in y direction, look at this figure. So this will be the component in z direction. Then none of the other plane forces has component in z direction due to initial curvature. Only this curvature effect will be there, that is shown in the equation above. However, all the in-plane forces have z component due to curvature that result from bending. Thus the z component of the in-plane forces for cylindrical shell element are obtained by adding the terms used in the equilibrium equation for plates and for shell in z direction as follows. So now we are going to combine the forces in x and y direction and the z direction as we shown above. So now we are going to combine this. So after combining this, we will get the whole this equation. Then to the z component of the in-plane forces must be added to the transverse shear forces, that is given by this second equation. So the transverse shear forces will be given by this equation. Then next coming to the moments, since the equation of moment equilibrium about x and y axis do not change, and in going to form the plate to the shell element, the shear forces in above equation can be rewritten in the form of. So because of moment equilibrium, the shear forces that we considered here in this slide, this equation will turn to this. So it can be rewritten in this form. And now finally we are going to combine all the terms to obtain the equation of equilibrium in z direction. So finally we'll be getting this equation: d square mx by dx square minus 2d square mxy dou x dou y plus dou square my by dou y square plus nx dou square y by dx square plus 2 nxy dou square y by dou x dou y plus ny in bracket 1 by r plus dou square w by dou y square equals to 0. So this will be our final equation of equilibrium for cylindrical shell. Thank you.